In the last video, we established that manipulator robots are built from two fundamental joint types: Revolute joints that rotate and prismatic joints that slide. Every joint in the robot contributes exactly one number to the robot's description. That's an angle for Revolute and a displacement for prismatic. And the sequence of those joints, written as R's and P's from the base to the tip, gives the robot its name. That's a clean picture, but it's not the full picture, because those two types are not the only joints that can exist. There are more complex joints out there, and the reason they matter is not just that they appear in real machines. It is what they reveal about how joint motion actually works. Specifically, they reveal something that is easy to miss when you only look at Revolute and prismatic in isolation. Every more complex joint type is actually a combination of Revolute and prismatic joints acting at the same location. That's the central idea of this video. Let's build to it properly. The first thing we need is a precise way to count the ways in which a joint can actually move. And to help us do this, we actually use a concept called degrees of freedom. A degree of freedom is any independent direction of motion available at a joint. A Revolute joint has one. It rotates about its axis and nothing else. A prismatic joint also has one. It slides along an axis and nothing else. One motion, one degree of freedom, one joint variable, which we write as Q to help us describe that particular motion. The joint variable Q is simply the number that describes where the joint currently is. For Revolute joints, Q is an angle. For prismatic joints, Q is a distance. The whole state of the robot, everything you need to know to draw it precisely, is captured by a vector of all of its joint variables. That vector is going to follow us for the rest of this course. Now, what happens when you allow more than one of these motions at the same location? Consider a telescope. The barrel rotates about its axis, so you can technically point it at any azimuth. It also slides along the same axis, so you can extend or retract the tube to adjust the focus of the telescope. Those two motions are completely independent. Rotating does not cause the tube to extend, and extending does not cause it to rotate. You can do each one without touching the other. This is actually a cylindrical joint. It has 2 degrees of freedom because you have two different things that you can control. That means it has two joint variables. And the key insight is that a cylindrical joint is not a fundamentally new thing. It's just a Revolute joint and a prismatic joint sharing the exact same axis. The rotation is one joint of freedom and the translation is the other, and they happen to live in the exact same place, hence one single joint. You could model a cylindrical joint with two separate 1 DOF joints stacked at the same location, and you would get the exact same mathematics. The cylindrical joint is just a compact name for that combination. Now consider something different. Think about driving a screw into a piece of wood. As you rotate the screwdriver, the screw moves forward. You cannot rotate it without translating, and you can't translate it without rotating. The two motions are coupled. They're locked together by the geometry of the thread. This is actually called a helical joint. It also has a rotation and a translation along the same axis. So at first, it does look similar to a cylindrical joint, but it only has 1 degree of freedom and not 2. The coupling between the rotation and the translation means that one number, which is the helix angle, is enough to tell us the actual displacement as well and describe everything. One motion drives the other. That coupling is what makes a helical joint different, and it's also what makes them a little harder to work with mathematically. And for that reason, helical joints are not something that we'll model in this particular course. They exist and they're important in real machines, so it's definitely worth knowing what they are. But the constraint that ties rotation to translation puts them outside the framework that we're building here, which is clean independent joint variables, one per degree of freedom, and nothing more. What if instead of one rotational axis, you want all three? Your shoulder is the closest example. It can swing forward and back, swing side to side, and rotate along the length of your arm. That's 3 independent rotational directions, all operating through the same joint center. This is a spherical joint. It's also called a ball and socket joint. 3 degrees of freedom, 3 joint variables, all rotational. Again, it's not a new primitive. is just three Revolute joints that are originating at the exact same point, each about a different axis. The spherical joint is just a compact name for that combination. Three independent rotations at one location. And that's actually the maximum rotational freedoms that any joint can possibly have. Finally, imagine a flat ice hockey puck, which is sliding on a frictionless ice surface. It can move forward and backward, and it can also move left and right. Apart from that, it can also spin in place. That's three independent motions, two translations, and one rotation, all within the same plane. This is a planar joint. That's 3 degrees of freedom. Two prismatic, one revolute, all sharing the same location. So it also follows the exact same principle. So here's what the full picture looks like. A revolute joint is just one rotation about an axis. That means it has 1 degree of freedom. Similarly, a prismatic joint is just one translation along one particular axis. So it too has only 1 degree of freedom. However, more complex joints do exist, such as a cylindrical joint that has one rotation and one translation along the same axis independently. Therefore, it actually has 2 degrees of freedom. Similarly, we have other joints like a spherical joint that has 3 independent rotations about the same point, giving it 3 degrees of freedom, and also a planar joint that has 2 independent translations and 1 rotation, all within a plane, hence 3 degrees of freedom. Other complex joints do exist, like the helical joint that has 2 types of motion, but since they're coupled together, they only have 1 degree of freedom. And there are many more that we're just not covering in this particular course. Every single one of the more complex types of joints is actually just a combination of R and P joints at the same location. So the cylindrical joint is just an RP collapsed onto one axis. The spherical joint is just a 3R that's collapsed onto one point. And the planar joint is just PPR or 2P, 1R collapsed onto a plane. And this is not just a neat observation. It's the reason that the mathematics of this course stays tractable. No matter how complex a joint looks mathematically, you can always decompose it into its constituent R and P components. Count the degrees of freedom, and you can identify the joint variables and write down the mathematics in exactly the same framework. 1 degree of freedom requires exactly one number to describe its entire state, which means it can be described with just one variable, and hence it gets one particular Q. That structure holds everywhere. The next video steps back from individual joints and looks at complete robot configurations. Because once you know what types of joints exist and how they combine, the natural question is how you could combine those joints to actually allow your end effector to reach different points in space. And the answer turns out to depend almost entirely on which joints are revolute and which ones are prismatic, and in what order they're actually present. Every video in this course comes along with a hands-on interactive file that you can actually play around with to get an intuition for all of the topics that are being taught in that particular video. So in today's companion file, you actually get 3D models of different joint types that you can manipulate in real time using sliders. So for a cylindrical joint, for example, you might get 2 independent sliders, one for rotation and one for translation. And moving them separately makes the independence tangible in a way that description alone would not. So you can actually test out the degrees of freedom and see how each joint moves to get a clear description. This might feel like a small idea right now, just some joint types and degree of freedom counts. But what you've just learned is the actual alphabet of robotics. Everything in this course, the kinematics, the motion planning, the control, will all be written in this language. And the fact that you're able to understand it now definitely makes you ready to take on the task of robotics and who knows, one day make the next robot that might change the world.